As you sit watching this video, something extraordinary is happening. Something so bizarre, so counterintuitive, that when scientists first discovered it, they refused to believe their own data. Right now, at this very moment, the edge of the observable universe is racing away from you at a speed that would make light itself look like a crawling snail. We are talking about speeds exceeding 670 million miles per hour. We are talking about galaxies that are moving away from us at 3 times the speed of light. And here is what makes this truly insane. This is not a theory. This is not speculation. This is measured, confirmed, observed reality. But wait, every physics textbook, every science class, every documentary you have ever watched has told you one fundamental rule. Nothing can travel faster than the speed of light. Einstein said it. The equations prove it. The experiments confirm it. Nothing, absolutely nothing, can break this cosmic speed limit. So how is it possible that the edge of the universe is doing exactly that? Is Einstein wrong? Did we miss something? Or is there something far stranger going on? Something that challenges our very understanding of what space, time, and motion actually mean. Let me tell you right now, the answer to this question is one of the most beautiful, most elegant, and most terrifying revelations in all of modern physics. And by the end of this video, you will not only understand how the universe breaks its own speed limit, you will understand why it must, why the math demands it, and what this means for the ultimate fate of everything that exists. Today we are going deep. We are going to explore the true nature of cosmic expansion, the mathematical framework that allows superluminal recession, the discovery that shocked the entire scientific community in 1998, the mysterious force called dark energy that is accelerating everything into oblivion, the quantum nature of empty space, the difference between the observable universe and the actual universe, cosmic horizons that imprison us forever, and the ultimate fate that awaits every star, every galaxy, every atom in existence. This is not a surface-level explanation. This is the full picture, from every angle, backed by real research, real data, and real physics. Before we dive in, if you are the kind of person who loves exploring the deepest mysteries of the cosmos, if your brain craves understanding, then hit that subscribe button right now. Tap the like button and drop a comment telling me what you think is beyond the edge of the observable universe. Trust me, you are going to want to be here for what comes next. Now let me take you back to a moment that changed everything we thought we knew about the cosmos. The year was 1998. 2 independent teams of astronomers were engaged in one of the most ambitious observation campaigns in the history of science. The first team was called the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The second team was called the High Z Supernova Search Team, led by Brian Schmidt and Adam Riess. These 2 groups were competitors. They were racing each other to answer what seemed like a straightforward question. Everyone already knew the universe was expanding. Hubble had proven that back in 1929. But the big question in the late 1990s was simple. How fast is the expansion slowing down? You see, at that time, every cosmologist expected the same answer. The universe exploded outward in the Big Bang. Gravity has been pulling everything back together ever since. Therefore, the expansion must be decelerating. The only question was how quickly. Was it slowing down fast enough to eventually reverse and collapse back into a big crunch? Or was it slowing down gradually, destined to coast forever, but never quite stop? Those were the only 2 options anyone seriously considered. Nobody, and I mean nobody, expected what these 2 teams actually found. Their method was brilliant. They used a specific type of stellar explosion called a Type 1a supernova. These are special because they always explode with almost exactly the same intrinsic brightness. Think of it like a standardized light bulb. If you know a light bulb is exactly 100 watts, and you measure how dim it looks from where you are standing, you can calculate exactly how far away it is. The dimmer it appears, the farther away it must be. Type 1a supernovae work the same way. By measuring how bright they appeared versus how bright they should be, astronomers could determine their precise distances. Then by measuring the redshift of the host galaxies, they could determine how fast those galaxies were moving away. Combine distance with velocity across cosmic time, and you get the expansion history of the universe. Both teams collected data from dozens of distant supernovae. Both teams ran their analyses independently. And both teams got the same shocking result. The distant supernovae were dimmer than they should have been. Not by a tiny amount, but by a significant, statistically undeniable margin. This meant they were farther away than expected. And the only way they could be farther away than expected is if the expansion of the universe is not slowing down at all. It is speeding up. Let me repeat that, because it deserves emphasis. The expansion of the universe is accelerating. The universe is not gently coasting outward after the Big Bang. It is pressing the accelerator. Every second, the expansion gets faster. Every moment, space grows more rapidly than the moment before. This was, without exaggeration, one of the most unexpected and revolutionary discoveries in the entire history of physics. Both teams checked and rechecked their data for months. They looked for errors, calibration problems, dust contamination, anything that could explain away the result. Nothing worked. The data was clear. The universe is accelerating. When this discovery was published, the scientific community was stunned. This meant that some unknown force, some mysterious energy, was pushing space apart against the pull of gravity. This unknown force was eventually named dark energy, and it changed everything. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Riess were awarded the Nobel Prize in Physics for this discovery. And the implications of what they found are directly connected to why the edge of the universe moves faster than light. Now, to truly understand what is happening at the edge of the universe, we need to build our understanding from the ground up. We need to start with the most fundamental question. What is the speed of light, and why is it a limit? The speed of light in a vacuum is exactly 299,792,458 meters per second. This is not an approximation. Since 1983, this value has been defined as exact, because the meter itself is defined in terms of how far light travels. This speed is approximately 300,000 kilometers per second, or about 186,000 miles per second. At this speed, light can circle the entire Earth 7.5 times in a single second. Light from the Sun takes 8 minutes and 20 seconds to reach us. Light from our nearest neighboring star, Proxima Centauri, takes 4 years and 3 months to reach us. Light from the Andromeda Galaxy, our nearest large galactic neighbor, takes 2.5 million years to reach us. Now here is why this speed is special. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper that would rewrite the laws of physics. His special theory of relativity contained 2 seemingly simple postulates. First, the laws of physics are the same in all inertial reference frames. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. From these 2 simple starting points, Einstein derived consequences that shattered our intuitions about space and time. One of the most profound consequences is this. As an object with mass accelerates closer and closer to the speed of light, its relativistic mass increases. The closer it gets to light speed, the more massive it becomes. At 90% the speed of light, its mass has roughly doubled. At 99%, it has increased by a factor of about 7. At 99.99%, it has increased by a factor of over 70. And as it approaches the speed of light exactly, its mass approaches infinity. This means the energy required to accelerate it further also approaches infinity. You would need literally infinite energy to push a massive object to the speed of light. Since infinite energy does not exist, no massive object can ever reach light speed. This is not a technical limitation. It is not that our rockets are not good enough. It is a fundamental law of nature, woven into the very fabric of reality. But here is the critical point, the point that most people miss, the point that makes the entire puzzle of superluminal expansion solvable. Einstein's speed limit applies to objects moving through space. It applies to particles, rockets, signals, information traveling through the fabric of space-time. It says nothing about space itself. Space is not an object. Space is not a thing moving through space. Space is the arena in which things exist. And it turns out, the arena itself has no speed limit. This distinction is everything. Let me repeat it, because it is the key to this entire video. Nothing can travel through space faster than light. But space itself can expand at any rate it wants, and there is no law of physics that prevents it. General relativity, Einstein's own masterwork published in 1915, describes gravity not as a force, but as the curvature of space-time caused by mass and energy. In general relativity, the geometry of space can change. Space can curve, warp, stretch, and yes, expand. And the rate of that expansion is governed by the contents of the universe, the matter, radiation, and energy within it, not by the speed of light. Now, let me take you back further in history to understand how we first discovered that space is expanding at all. The story begins with a man whose name is now synonymous with cosmic expansion: Edwin Hubble. In the early 1920s, astronomers were embroiled in what is now called the Great Debate. On one side was Harlow Shapley, who argued that the Milky Way was the entire universe, and that the fuzzy spiral patches visible through telescopes were merely nearby gas clouds within our galaxy. On the other side was Heber Curtis, who argued that these spiral patches were actually entire galaxies like our own, vast and incredibly distant. The debate was resolved in 1924 when Edwin Hubble, using the powerful 100-inch Hooker telescope at Mount Wilson Observatory, identified a special type of pulsating star called a Cepheid variable in the Andromeda Nebula. Cepheid variables have a known relationship between their pulsation period and their intrinsic luminosity. By measuring the period of this Cepheid in Andromeda, Hubble could determine its true brightness. By comparing that to its apparent brightness, he could calculate its distance. The answer was staggering. Andromeda was approximately 900,000 light-years away, far beyond the boundaries of the Milky Way. The spiral nebulae were not gas clouds. They were entire galaxies, each containing billions of stars, separated from us by almost incomprehensible distances. The universe was suddenly vastly larger than anyone had imagined. But Hubble's greatest discovery was yet to come. By 1929, Hubble had measured both the distances and the velocities of dozens of galaxies. He measured their velocities using a phenomenon called redshift. When a light source moves away from you, the light waves get stretched out, shifting toward the red end of the spectrum. The faster the source recedes, the greater the redshift. What Hubble found when he plotted galaxy distance against galaxy velocity was remarkable. There was a clear, linear relationship. The farther away a galaxy was, the faster it was moving away from us. This was not just a trend. It was a precise proportionality. A galaxy twice as far away was receding twice as fast. A galaxy 3 times as far was receding 3 times as fast. This relationship is now called Hubble's law, and it is expressed by one of the simplest yet most profound equations in all of cosmology. Velocity equals h0 times distance. V equals h0 times d. Here, h0 is the Hubble constant, which tells you the expansion rate. Its current best measured value is somewhere between 67 and 73 kilometers per second per megaparsec, where a megaparsec is about 3.26 million light-years. What this equation tells you is stunningly simple. For every megaparsec of distance between us and a galaxy, that galaxy is receding at roughly 70 kilometers per second. Now here is where it gets mind-bending. This is a linear relationship with no maximum. There is no cap. If a galaxy is 100 megaparsecs away, it recedes at 7,000 kilometers per second. If it is 1,000 megaparsecs away, it recedes at 70,000 kilometers per second. If it is 4,280 megaparsecs away, it recedes at roughly 300,000 kilometers per second, which is the speed of light. And if it is farther than that, its recession velocity exceeds the speed of light. Let that sink in. Hubble's law, a simple linear equation confirmed by nearly a century of observations, mathematically guarantees that beyond a certain distance, galaxies recede faster than light. This distance is called the Hubble radius, or the Hubble sphere, and it is currently about 14.4 billion light-years away from us in comoving coordinates. Everything beyond this sphere is moving away from us faster than light. And given the size of the observable universe, which stretches 46.5 billion light-years in every direction, the vast majority of the observable universe is already receding from us at superluminal speeds. Let me emphasize something profound. This is not some exotic edge case physics. This is the straightforward, inevitable consequence of uniform expansion. If expansion is the same everywhere, then there must be a distance beyond which the cumulative expansion rate exceeds light speed. There is no way around it. It is simple mathematics. But you might ask a very reasonable question. If these galaxies are receding faster than light, how can we see them? If their light can never reach us because they are moving away faster than light, how do we even know they exist? This is a brilliant question, and the answer reveals another layer of the beauty of cosmic expansion. When we observe a very distant galaxy, we are not seeing it as it is now. We are seeing it as it was when it emitted the light that is now reaching us. Billions of years ago, when that galaxy emitted the photons we are currently detecting, it was much closer to us. The recession velocity at that earlier time, when the galaxy was nearer, was less than the speed of light. So the light was able to travel toward us. As the light traveled, space expanded behind it, carrying the galaxy farther and farther away. By the time the light finally reaches us today, the galaxy has been carried by expansion to a distance where it is now receding faster than light. But the light that we see left the galaxy long ago, when the galaxy was still within a more reasonable distance. Think of it like this. Imagine you throw a message in a bottle into the ocean. After you throw it, a powerful current sweeps you far away, faster and faster. By the time someone picks up the bottle, you might be thousands of miles away, moving faster than the bottle ever traveled. But the bottle still reached them because it was thrown when you were close. That is essentially what is happening with the light from distant galaxies. There is another subtlety here. In an expanding universe, a photon that enters a region of space where the expansion rate exceeds light speed does not stop moving forward in some local sense. Locally, photons always travel at the speed of light relative to their immediate surroundings. but if the space in front of the photon is expanding faster than the photon can cover it. The photon effectively makes no net progress toward its destination, or even loses ground. It is like trying to run up a treadmill that is speeding up. You are running at full speed locally, but the belt beneath you is moving faster, so you slide backward. For many photons emitted from distant galaxies today, this is exactly their fate. They will travel at the speed of light through their local space forever, but they will never reach us because the expansion of the space between us and them is simply too fast. This brings us to one of the most important concepts in cosmology, the concept of cosmic horizons. And trust me, this is where things get truly deep. There are several types of cosmic horizons, and understanding them is crucial to understanding the true structure of the universe we inhabit. The first is the particle horizon. This is the maximum distance from which any signal, traveling at the speed of light since the very beginning of the universe, could have reached us by now. It defines the boundary of our observable universe. Its current radius is about 46.5 billion light-years in comoving distance. You might wonder how the observable universe can be 46.5 billion light-years in radius if the universe is only 13.8 billion years old. After all, shouldn't light have only traveled 13.8 billion light-years? Now, and this confusion arises from forgetting about expansion. A photon emitted by a galaxy 13 billion years ago indeed traveled for 13 billion years. But during those 13 billion years, the space between us and that galaxy kept expanding. By the time the photon arrives, the galaxy has been carried far beyond 13 billion light-years away. It is now perhaps 30 or 40 billion light-years away. The 46.5 billion light-year radius represents the current distance to objects whose ancient light is just now arriving. The second type of horizon is the cosmological event horizon. This is subtly different and in some ways more profound. The event horizon represents the maximum distance from which a signal emitted right now, today, can ever reach us in the entire future of the universe, even given infinite time. In a universe with decelerating expansion, there would be no event horizon, because eventually any signal could reach us if we waited long enough. But in a universe with accelerating expansion, like ours, the event horizon exists and is actually shrinking. Currently, our cosmological event horizon is at a comoving distance of approximately 16 billion light-years. This means that any galaxy currently beyond 16 billion light-years from us, even if it sends a signal right now, that signal will never, ever reach us. No matter how long we wait, the expansion of the space between us will outpace the light forever. And here is the truly terrifying implication. Because expansion is accelerating, this event horizon is getting closer. More and more galaxies are crossing this boundary every moment. Once a galaxy crosses our event horizon, it is gone forever. No signal from it will ever reach us again. The last photons from that galaxy will be progressively redshifted, becoming dimmer and redder, and eventually fading beyond any possible detection. From our perspective, the galaxy gradually freezes, dims, and disappears. It does not flash out of existence. It fades into eternal silence. Now I want you to appreciate the scale of what I am describing. The observable universe contains roughly 2 trillion galaxies. Of these 2 trillion galaxies, approximately 97% are already beyond our reach. Even if we could build a spacecraft traveling at the speed of light, right now, today, we could never reach them. The expansion has already won. They are gone. And every day, the number we can reach shrinks further. Let me put this differently. Imagine all the galaxies in the observable universe as cities on a map. Our galaxy, the Milky Way, sits at the center of our map. Out of 2 trillion cities on this map, we can potentially visit maybe 60 billion, about 3% of the total. And that number is decreasing. Every second, cities are disappearing off the edge of our accessible map. Never to be visited, never to be contacted, never to be known in person. Now, let us talk about the physical mechanism driving this expansion. What actually causes space to expand? To understand this, we need to go back to Einstein's general relativity and the equations that describe the evolution of the universe. In 1915, Einstein completed his general theory of relativity. This theory describes gravity not as a force acting at a distance as Newton had proposed, but as the curvature of 4-dimensional spacetime caused by the presence of mass and energy. Matter tells space how to curve. Space tells matter how to move. The equations of general relativity relate the geometry of spacetime to the distribution of mass and energy within it. When you apply these equations to the universe as a whole, assuming the universe is roughly uniform and the same in all directions on large scales, which observations confirm, you get a set of solutions called the Friedmann equations, named after Alexander Friedmann, who derived them in 1922. The Friedmann equations describe how the scale factor of the universe, essentially a number representing the relative size of the universe, changes over time. They tell us how fast the universe is expanding and how that expansion rate changes depending on what the universe contains. If the universe contains only matter, expansion decelerates because gravity pulls matter together. If the universe contains radiation, expansion decelerates even faster because radiation contributes additional pressure. But if the universe contains something with negative pressure, something that pushes rather than pulls, then expansion accelerates. This is exactly what dark energy does. Dark energy has the bizarre property of having negative pressure. In general relativity, pressure contributes to gravitational effects. Normal positive pressure adds to gravitational attraction. But negative pressure does the opposite. It creates gravitational repulsion. Dark energy has so much negative pressure that its repulsive gravitational effect overwhelms its attractive effect, driving the universe into accelerated expansion. The most popular candidate for dark energy is the cosmological constant. Originally introduced by Einstein in 1917 and represented by the Greek letter lambda, Einstein added this constant to his field equations to create a static universe, because at that time, everyone believed the universe was eternal and unchanging. When Hubble discovered expansion in 1929, Einstein reportedly called the cosmological constant his biggest blunder and removed it. The irony is almost poetic. 70 years later, the supernova teams discovered that not only is the cosmological constant real, it dominates the energy content of the entire universe. The cosmological constant represents a constant energy density that fills all of space uniformly. It does not dilute as space expands. When you double the volume of space, you get double the total dark energy, because the energy density per unit volume stays the same. This is radically different from matter, whose density decreases as space expands, because the same amount of matter is spread over a larger volume. It is also different from radiation, whose density decreases even faster because photons lose energy as their wavelengths stretch with expansion. This non-diluting property is what makes dark energy so powerful and so terrifying. As the universe expands, matter and radiation become less and less important because they are spread thinner and thinner. But dark energy remains constant. Given enough time, dark energy inevitably dominates, and once it dominates, its repulsive gravity drives exponential expansion. We are currently living in the era when dark energy has taken over. Approximately 5 billion years ago, dark energy surpassed matter as the dominant component of the universe. Since then, cosmic expansion has been accelerating. Today, the energy budget of the universe is approximately 68% dark energy, 27% dark matter, and about 5% ordinary matter. That means everything you have ever seen, every star, every planet, every person, every atom of normal matter makes up only 5% of what the universe contains. The vast majority is invisible, mysterious, and barely understood. Now let us talk about the math in slightly more detail, because understanding the math makes the superluminal recession feel less like magic and more like an inevitable logical consequence. The metric that describes our expanding universe is called the Friedmann-Lemaitre-Robertson-Walker metric, or flow metric for short. In this framework, the universe is described using what are called comoving coordinates. These are coordinates that expand along with the universe. An object sitting still in the expanding universe, not moving relative to the cosmic flow, maintains constant comoving coordinates even as the physical distances between objects grow. The physical distance between two comoving objects at any given time is simply their comoving distance multiplied by the scale factor at that time. The scale factor is a dimensionless number that describes how much the universe has expanded since some reference time. If we set the scale factor to 1 today, then it was about 1/1000th at the time the cosmic microwave background was emitted, about 380,000 years after the Big Bang. This means the universe was 1,000 times smaller in every direction at that time. The recession velocity of a distant galaxy is simply the rate of change of the physical distance between us, which equals the comoving distance times the rate of change of the scale factor. This is Hubble's law in disguise. The Hubble parameter at any time equals the rate of change of the scale factor divided by the scale factor itself. And because comoving distance can be any value, the recession velocity, which is comoving distance times the Hubble parameter, can also be any value. There is no cap at the speed of light. The math does not impose one, because this is not motion through space. It is the expansion of space itself. Let me give you a concrete example with real numbers. Consider a galaxy at a current comoving distance of 10,000 megaparsecs. Using a Hubble constant of 70 kilometers per second per megaparsec, its recession velocity is 70 times 10,000, which equals 700,000 kilometers per second. That is more than twice the speed of light. This galaxy exists within our observable universe. We can see the ancient light it emitted billions of years ago. But right now, at this moment, it is flying away from us at more than twice the speed of light due to expansion. The most distant galaxy candidates detected by the James Webb Space Telescope have redshifts exceeding 13. At a redshift of 13, the recession velocity at the time the light was emitted was actually superluminal. The galaxy was already receding faster than light when it sent out the photons we are now detecting. Those photons were initially swept backward by expansion, but later, as they entered regions of space where the local expansion rate was lower, they were able to make forward progress and eventually reach us. This is another mind-bending detail. We are actually observing light from galaxies that were moving away from us faster than light at the moment of emission. The photons were essentially swimming against a current, losing ground initially, then gaining ground later as they moved into regions with less expansion between them and us. Now I want to take us into even deeper territory. We have established that space is expanding, that the expansion is accelerating, and that distant galaxies recede faster than light. But what exactly is space? What is this thing that is expanding? This is where we enter one of the deepest open questions in all of physics. In classical physics, space was considered a passive, static stage on which events unfold. It was the background, the container, the emptiness between things. Newton imagined absolute space as a fixed framework, unchanging and eternal. But general relativity changed this completely. In Einstein's theory, space is not passive. It is dynamic. It curves in response to matter. It ripples in the form of gravitational waves. And as we now know, it expands. Space in general relativity is more like a fabric than a stage, a fabric that can be stretched, compressed, warped and deformed. But when we zoom in to the quantum level, things become even stranger. Quantum mechanics tells us that empty space is not actually empty. Even a perfect vacuum, with all matter and radiation removed, seethes with activity at the smallest scales. This is because of the Heisenberg uncertainty principle. You cannot simultaneously know the exact value of a quantum field and its rate of change. This means quantum fields can never be perfectly zero everywhere. They must fluctuate. These fluctuations are called vacuum fluctuations or zero-point fluctuations, and they have real, measurable consequences. The most famous demonstration of vacuum fluctuations is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed in 1997. If you place two uncharged metal plates extremely close together in a vacuum, fewer types of vacuum fluctuations can fit between the plates than exist outside them. This creates a net inward pressure, pushing the plates together. This force has been measured with remarkable precision and matches the theoretical prediction. It proves that the vacuum is not truly empty. It buzzes with quantum activity. Now here is where this connects to expansion and dark energy. One natural explanation for dark energy is that it is the energy of the quantum vacuum. Empty space has inherent energy due to these quantum fluctuations, and this energy acts as a cosmological constant driving expansion. This is an elegant idea, but it has a catastrophic problem. When physicists calculate the expected vacuum energy using quantum field theory, they get an answer that is approximately 10 to the power of 120 times larger than the observed value of dark energy. Let me write that out. The predicted value is a 1 followed by 120 zeros times larger than what we actually measure. This is not a small discrepancy. It is the largest disagreement between theory and observation in all of science. It has been called the worst prediction in the history of physics. This enormous mismatch is known as the cosmological constant problem, and it remains unsolved. Some physicists believe there must be some unknown mechanism that cancels almost all of the vacuum energy, leaving only the tiny residual we observe as dark energy. Others think our calculation of vacuum energy is fundamentally flawed in some way we do not yet understand. Others still invoke the anthropic principle, arguing that only a universe with a very small cosmological constant could form galaxies, stars, and observers like us. So of course we find ourselves in such a universe. None of these explanations is fully satisfying, and the cosmological constant problem remains one of the greatest open puzzles in theoretical physics. Now let us go even deeper into the quantum nature of space. At the very smallest scales, at what is called the Planck scale, roughly 10 to the minus 35 meters, our current theories of physics break down completely. At this scale, quantum effects become so powerful that the smooth, continuous spacetime of general relativity dissolves into something else entirely. What that something else is, we do not yet know for certain. But several theories offer tantalizing hints. One idea, proposed by the great physicist John Wheeler in 1955, is quantum foam. At the Planck scale, Wheeler suggested space-time is not smooth. It is turbulent, chaotic, foaming with quantum fluctuations so intense that the very notion of distance and direction becomes meaningless. Space might be constantly forming and destroying tiny wormholes, black holes, and geometric deformations at this scale. If you could somehow zoom in enough, the smooth fabric of space would reveal itself to be a seething, roiling chaos. Another approach comes from a theory called loop quantum gravity. In this framework, space itself is quantized, meaning it comes in discrete chunks. Just as matter is made of atoms and energy comes in quantum packets called photons. Space itself may be made of tiny discrete units called quanta of area and volume. The smallest possible volume of space would be roughly 1 Planck volume, about 10 to the minus 105 cubic meters. Space, in this view, is not infinitely divisible. It has a granular structure at the very smallest scales, like pixels on a screen that appear smooth from a distance. If space is quantized, then what does it mean for space to expand? Does expansion create new quanta of space between existing ones? Do the individual quanta themselves grow? These questions do not yet have definitive answers, but they highlight how deeply mysterious expansion really is. When we say space is expanding, we are describing something that we can measure precisely, predict accurately, and observe clearly, but whose fundamental microscopic mechanism remains genuinely unknown. Let us now turn to another extraordinary episode of superluminal expansion, one that happened not at the distant edges of the universe today, but at the very beginning of time. I am talking about cosmic inflation. In 1980, a young physicist named Alan Guth at the Stanford Linear Accelerator Center proposed a radical idea. He suggested that in the first unimaginably tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion so extreme that it dwarfs anything we observe today. During inflation, the universe expanded by a factor of at least 10 to the 26 in a time interval of roughly 10 to the minus 32 seconds. Let me put that in perspective. In a time span so short that it makes a nanosecond look like an eternity, the universe went from being smaller than a proton to being larger than a grapefruit, and it did so at rates that make the current superluminal expansion look glacial by comparison. During inflation, the expansion rate was so extreme that regions of space were being separated at speeds that exceeded the speed of light by a factor of roughly 10 to the 43. Now, inflation happened incredibly early, before atoms existed, before even protons or neutrons existed. At that moment, the universe was a superhot, superdense plasma of quarks, gluons, and other fundamental particles. And inflation did not violate Einstein's speed limit for the same reason today's expansion does not. Nothing was moving through space faster than light. Space itself was expanding at a phenomenal rate. Guth proposed inflation to solve several major problems in cosmology. The first is called the horizon problem. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that it has almost exactly the same temperature in every direction, to a precision of about 1 part in 100,000. But regions on opposite sides of the sky are so far apart that without inflation, they could never have been in causal contact. Light has not had enough time since the Big Bang to travel between them. How can they have the same temperature if they have never communicated? It is like finding that two people on opposite sides of the world have independently written the exact same novel word for word. Without some connection between them, it is inexplicable. Inflation solves this elegantly. Before inflation, these regions were actually in close contact. They had time to reach thermal equilibrium, to equalize their temperatures. Then inflation blew them apart so rapidly that they ended up on opposite sides of the observable universe. They share the same temperature because they were once neighbors, before inflation separated them at superluminal speeds. Part 2. The second problem inflation solves is the flatness problem. Observations tell us that the geometry of the universe is flat to extraordinary precision. Not curved like a sphere, not curved like a saddle, but flat like a sheet of paper. In general relativity, the curvature of the universe depends on its total energy density. For the universe to be flat, the energy density must equal a very specific value called the critical density. And it does, to within 0.5%. But here is the problem. In a non-inflationary universe, flatness is unstable. Any tiny deviation from perfect flatness in the early universe would have grown enormously over time. For the universe to be as flat as we observe today, it would have had to start with a flatness tuned to 1 part in 10 to the 60 at the Planck time. This seems absurdly fine-tuned. Inflation solves this because exponential expansion drives any initial geometry toward flatness, just as inflating a balloon makes its surface appear flatter and flatter to an ant sitting on it. No matter what curvature the universe started with, inflation would have smoothed it out and stretched it flat. The evidence for inflation is strong, though indirect. The precise pattern of temperature fluctuations in the cosmic microwave background, as measured by the COBE, double map, and Planck satellites, matches the predictions of inflationary theory with remarkable precision. The tiny density fluctuations that inflation predicts, generated by quantum fluctuations stretched to cosmic scales, seeded the formation of all the large-scale structure we see today: galaxy clusters, filaments, and voids. Without inflation, we cannot easily explain why the universe has the structure it has. Some physicists have described the current epoch of dark energy-driven acceleration as a very weak version of inflation. During the original inflation, the universe expanded exponentially with an enormous rate constant. Today, the universe is again expanding exponentially, but with a vastly smaller rate constant. We are living in a second inflationary epoch. A slow, gentle inflation that will nonetheless have profound consequences over cosmic timescales. Now, I want to address something that many people find confusing. If space is expanding everywhere, why are we not expanding? Why is the Earth not getting bigger? Why is the solar system not flying apart? Why do galaxies still hold together? This is an excellent question, and the answer reveals something important about the nature of expansion. On small scales, the forces that hold structures together, gravity, electromagnetism, and the nuclear forces, are vastly stronger than the expansion effect. Expansion is trying to push everything apart, but on the scale of atoms, planets, solar systems, and even galaxies. The binding forces overwhelm expansion completely. Think of it like this. Imagine the universe as a vast ocean, with a slow, steady current flowing outward in every direction. Now imagine that scattered throughout this ocean are boats connected by ropes of various strengths. Some boats are connected by steel cables, some by thick ropes, some by thinner ropes. The ocean current, the expansion, is trying to pull all boats apart. But as long as the current is weaker than the ropes, the boats stay connected. They do not expand. Only on scales where no force holds things together, on scales of hundreds of millions of light years, where galaxies are not gravitationally bound to each other, does expansion win. In the vast voids between galaxy clusters, there is nothing to resist expansion, and so space stretches freely. This is why the universe expands on large scales while remaining stable on small scales. However, and this is crucial, if dark energy intensifies over time, a scenario called phantom dark energy, then eventually the expansion could become strong enough to overcome galaxy gravity. Then stellar gravity, then the electromagnetic forces holding atoms together. This doomsday scenario is called the Big Rip, and we will return to it later. Now, I want to bring us to one of the most profound aspects of this topic: the observable universe, versus the actual universe. This distinction is critical and rarely fully appreciated. Everything I have discussed so far concerns the observable universe, the sphere of space from which light has had time to reach us since the Big Bang. This sphere has a current radius of about 46.5 billion light-years. But the observable universe is not the whole universe. It is merely the part we can see. The actual universe extends beyond the observable universe, possibly far, far beyond. And the actual universe might be infinite. How can we know anything about the size of the actual universe if we cannot see beyond our observable sphere? We can make inferences from geometry. If the universe is perfectly flat, as observations strongly suggest, then it is either infinite or very nearly so. The Planck satellite's measurements of the cosmic microwave background place extremely tight constraints on the curvature of space. If the universe has any positive curvature at all, it must be so slight that the actual universe is at least 250 times larger than the observable universe in each direction. Some estimates, based on the most conservative interpretations of the data, suggest the actual universe could be at least 10 to the 23 times larger in volume than what we can observe. Other estimates say it is simply infinite. Let me try to convey what this means. The observable universe contains roughly 2 trillion galaxies and 10 to the 24 stars. If the actual universe is 10 to the 23 times larger, it contains roughly 10 to the 23 times more galaxies and stars. That is a number so large that within such a universe, every possible arrangement of atoms within a region the size of our observable universe would be repeated somewhere. There would be other regions that look exactly like ours, with exact copies of Earth, of you, of this moment. This is not science fiction. It is a straightforward mathematical consequence of a large enough universe with a finite number of possible particle arrangements. Of course, these copies would be so impossibly far away that no signal could ever bridge the gap. They are theoretical certainties that are observational impossibilities. And remember, all of this, all of the actual universe, whether finite or infinite, is expanding. Every point in it is getting farther from every other point. The superluminal recession we observe at the edge of our observable universe is happening everywhere, at every scale, between all sufficiently separated regions. The universe is not expanding from a center. There is no center. Every location is equivalent. Every observer sees the same thing, everything receding, with more distant objects receding faster. This is the nature of uniform expansion in a universe without a preferred center or edge. Let me now discuss the cosmic microwave background in more detail, because it provides our most powerful window into the early universe and directly reveals the expansion history. The CMB is light that was emitted approximately 380,000 years after the Big Bang, at a moment called recombination. Before this moment, the universe was so hot that electrons could not bind to atomic nuclei. Free electrons scattered photons continuously, making the universe opaque, like a thick fog. But as the universe expanded and cooled, it reached a temperature of about 3000 Kelvin, and electrons finally combined with nuclei to form neutral atoms. Suddenly, photons were free to travel without scattering. The fog cleared, and the universe became transparent. Those photons have been traveling freely ever since, for 13.8 billion years. But during their journey, the universe expanded enormously. Their wavelengths stretched by a factor of about 1080. What was once glowing hot radiation at 3000 Kelvin has been redshifted down to just 2.725 Kelvin, a faint microwave glow pervading all of space. This is the cosmic microwave background. It comes from every direction. It fills the universe. And its incredible uniformity, combined with its tiny fluctuations, tells us about the composition, geometry, and expansion history of the universe with extraordinary precision. The CMB also illustrates the concept of superluminal recession beautifully. The photons we detect from the CMB were emitted by matter that was, at the time of emission, only about 42 million light-years away from us. Not very far at all by cosmic standards. But today, that same matter, the matter that emitted the CMB photons we now detect, is roughly 46 billion light-years away. It has been carried outward by expansion. Its current recession velocity exceeds the speed of light by a factor of about 3. We are looking at light from matter that is now moving away from us at 3 times light speed. And yet the photons reached us, because they were emitted when the matter was close enough and the recession velocity was below light speed at the point of emission relative to the photon's path. Now, let us go deeper into the concept of redshift, because it is more subtle than most people realize. There are 3 types of redshift in physics. The first is Doppler redshift, caused by the actual motion of an object through space. The second is gravitational redshift, caused by photons climbing out of a gravity well. The third is cosmological redshift, caused by the expansion of space, stretching the wavelength of photons during their journey. When we observe distant galaxies receding at superluminal velocities, the redshift we measure is cosmological. It is not a Doppler effect. The galaxy is not moving through space at superluminal speed. Its space is simply expanding, stretching the photon wavelengths during their long journey. The distinction matters because it determines how we interpret the observations. A Doppler redshift of 3 would imply a velocity of about 95% of light speed. But a cosmological redshift of 3 means the universe has expanded by a factor of 4 since the light was emitted, and the current recession velocity may be well above light speed. The two are physically different phenomena that produce similar observational signatures. Misinterpreting cosmological redshift as Doppler shift has led to countless misconceptions in popular science. Now I want to take us to the very frontier of current research, to a puzzle that is actively baffling astronomers right now. It is called the Hubble tension, and it might be pointing us toward new physics that we do not yet understand. As I mentioned earlier, the Hubble constant tells us the current expansion rate of the universe. In principle, there is only one correct value for it. But when astronomers measure it using 2 different methods, they get 2 different answers that refuse to agree. The first method uses the cosmic microwave background, the Planck satellite, operated by the European Space Agency, mapped the CMB with extraordinary precision. From the detailed pattern of hot and cold spots, physicists can extract the full expansion history of the universe and predict what the current expansion rate should be. The answer from Planck is 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. The second method uses the traditional cosmic distance ladder. Astronomers measure distances to nearby galaxies using Cepheid variable stars, then use those calibrated distances to determine the brightness of Type 1 supernovae in those galaxies, and then use those calibrated supernovae to measure distances to much more remote galaxies. From this, they derive the expansion rate directly from local observations. The answer from this method, as reported by Adam Rees and colleagues, is 73.04 kilometers per second per megaparsec, also with very small uncertainty. The discrepancy between 67.4 and 73.0 is about 9%. This might sound small, but given the precision of both measurements, this disagreement has a statistical significance exceeding 5 sigma, meaning there is less than a 1 in a million chance it is due to random error. Both measurements have been checked, rechecked, and confirmed by multiple independent groups using multiple independent techniques. The tension appears to be real. This is genuinely exciting because it might be telling us that our standard model of cosmology is incomplete. Several possible explanations have been proposed. Maybe dark energy is not perfectly constant, but has changed slightly over time. Maybe there is a new type of particle or radiation that we have not accounted for. Maybe the early universe underwent a phase transition that slightly altered the expansion dynamics. Maybe gravity itself behaves differently on cosmological scales than general relativity predicts. Each of these possibilities would represent major new physics. The Hubble tension is one of the hottest topics in cosmology right now, and its resolution could fundamentally change our understanding of the universe. The James Webb Space Telescope, launched in December 2021, has provided valuable data relevant to this puzzle. JEST can observe Cepheid variables in more distant galaxies with greater precision than the Hubble Space Telescope, potentially clarifying whether the local distance ladder measurements are affected by systematic errors. Early JEST results have largely confirmed the higher value from the distance ladder, deepening the tension rather than resolving it. This suggests the discrepancy is not an observational artifact, but may genuinely point toward new physics. JEST has also made other discoveries that challenge our understanding of cosmic expansion and evolution. It has found galaxies at extremely high redshifts, corresponding to times less than 400 million years after the Big Bang, that are far more massive, more luminous, and more chemically evolved than our models predicted. These galaxies seem too big and too mature to have formed so quickly. While this does not directly contradict the expansion picture, it suggests that galaxy formation in the early universe was far more efficient than we thought, or that our timeline of cosmic evolution needs revision. Now I want to discuss something that sounds like science fiction, but is actually serious theoretical physics. Can we ever overcome cosmic expansion? Can we ever reach galaxies that are currently receding faster than light? Is there any conceivable technology that could outrun the expansion of space? In 1994, physicist Miguel Alcubierre proposed a theoretical framework for faster-than-light travel within general relativity. His idea, known as the Alcubierre warp drive, involves creating a bubble of warped spacetime around a spacecraft. Space would be compressed in front of the bubble and expanded behind it. The spacecraft inside the bubble would be at rest relative to its local space, thus not violating special relativity locally. But the bubble itself would move through the external space at any desired rate, potentially vastly exceeding the speed of light. This concept is mathematically valid within general relativity. The equations permit such a solution. However, the practical requirements are almost certainly impossible. The original Alcubierre metric requires exotic matter with negative energy density. The amount of negative energy needed in the original formulation was greater than the total mass energy of the observable universe. Subsequent refinements have reduced this requirement dramatically, but it still requires forms of energy that may not exist in nature. Even if a warp drive were possible, there is a deeper problem. You cannot use it to reach galaxies beyond the cosmological event horizon. The event horizon is not just a distance limit. It is a causal limit imposed by the structure of spacetime itself. A warp drive, being a solution within general relativity, must obey the causal structure of spacetime. And the causal structure of our accelerating universe says that beyond the event horizon, no future directed path, no matter how cleverly constructed, can connect us to that region. It is not a matter of speed, it is a matter of space-time geometry. Those regions are causally disconnected from our future, period. This leads to a haunting conclusion. The expansion of the universe imposes an absolute, fundamental, inescapable limit on exploration, communication, and knowledge. There are galaxies we can see, but never visit. There are galaxies we can visit now, but will not be able to visit if we wait too long. And there are galaxies already lost beyond our event horizon that will remain forever unknowable except through the ancient light they already sent us. The universe is like a library that is burning from the edges inward. The books at the margins are being lost one by one, and nothing can save them. Let me now talk about the implications of this expansion for the deep future of the universe. What happens as the accelerating expansion continues for billions, trillions, and incomprehensibly long timescales? If dark energy is indeed a cosmological constant, as current evidence most strongly supports, then the universe is headed toward what is called the heat death, or big freeze. This is not a sudden catastrophe. It is a slow, quiet, cold fading into eternal darkness. Let me walk you through the timeline. In about 4.5 billion years, the Andromeda Galaxy will collide and merge with the Milky Way. This merger will produce a larger elliptical galaxy that astronomers have nicknamed Milkdromeda or Milkomeda. During this collision, individual stars are so far apart that almost none will physically hit each other. But the gravitational interactions will dramatically reshape both galaxies, flinging some stars outward and causing others to fall toward the new combined center. New bursts of star formation will occur as gas clouds compress. Over the next 100 billion years or so, the local group, our small cluster of galaxies bound together by gravity, will merge into a single large galaxy. Meanwhile, every other galaxy and galaxy cluster in the universe, not bound to our local group, will be carried beyond our cosmic event horizon by the accelerating expansion. One by one, then in a flood, distant galaxies will fade and disappear, their light redshifting to undetectable wavelengths. By 100 billion years from now, an observer in Milkdromeda will see nothing outside their own galaxy. The sky beyond will be perfectly black. No other galaxy. No cosmic microwave background. Nothing. This observer will have no evidence that the Big Bang ever happened. They will have no evidence that other galaxies ever existed. They will look out and see only their own galaxy surrounded by eternal void. If they develop physics, they will logically conclude that the universe is static and that their galaxy is all that exists. And they will be wrong. But they will have no way to know they are wrong. This raises a deeply unsettling philosophical question. Are we in a similar position? Is there evidence of the universe's past or structure that has already been erased by expansion? Are we already missing crucial information about reality that was available to earlier observers? We do not currently have reason to believe so. We can still see the CMB, still detect distant galaxies, still reconstruct the expansion history. But the fact that future observers will be in exactly this position of ignorance should give us pause. The universe does not owe us completeness. It does not guarantee that the evidence for its own history will persist. Let us continue the timeline further. After all other galaxies disappear, star formation in Milkdromeda will gradually decline as the gas supply is exhausted. The last stars will form perhaps 100 trillion years from now. After that, no new stars will be born. Existing stars will burn through their fuel and die. Red dwarfs, the smallest and longest-lived stars, can burn for up to 10 trillion years. So by roughly 100 trillion years from now, the last red dwarf will flicker out. The universe will then enter what astronomers call the degenerate era. The only stellar remnants will be white dwarfs, neutron stars, and black holes. White dwarfs will slowly cool over trillions of years, gradually fading from white to yellow to red to infrared to invisible. Neutron stars will spin down and cool. Planets will drift in the dark, slowly spiraling away from their dead stars through gravitational radiation. Over truly enormous timescales, roughly 10 to the 37 to 10 to the 40 years, even these remnants will decay. If protons are unstable, as some grand unified theories suggest, then all ordinary matter will eventually decay into lighter particles, leptons and photons. Every white dwarf, every neutron star, every cold planet will dissolve into a thin haze of electrons, positrons, neutrinos and photons. After ordinary matter decays, black holes will reign supreme as the most complex objects in existence. But even black holes are not eternal. Stephen Hawking showed in 1974 that black holes emit thermal radiation due to quantum effects near their event horizons. This Hawking radiation causes black holes to slowly lose mass and eventually evaporate completely. Stellar mass black holes will take roughly 10 to the 67 years to evaporate. Supermassive black holes, like the ones at the centers of galaxies, will take approximately 10 to the 100th power years to evaporate. That number, 10 to the 100, is called a googol. After the last black holes evaporate in roughly 10 to the 100 years, the universe will contain only a thin, ever-dispersing gas of photons, electrons, positrons, and neutrinos, all flying away from each other in an ever-expanding void. The temperature will asymptotically approach absolute zero, but never quite reach it. Nothing will ever happen again in any meaningful sense. No complexity, no structure, no events, just eternal, expanding emptiness. The silence of an exhausted cosmos. This is the heat death. Not a dramatic explosion or collapse, but a gentle fading into permanent night. It is in many ways the most melancholy prediction in all of science, and it is driven directly by the same superluminal expansion we have been discussing. The expansion that carries galaxies beyond our reach will eventually isolate every particle from every other particle, stretching the distances between them to infinity over infinite time. Now, let me discuss the alternative scenario that is more dramatic, the Big Rip. This occurs if dark energy is not a constant but grows stronger over time, a possibility parameterized by what physicists call phantom dark energy, where the equation of state parameter W is less than -1. In this scenario, the expansion does not merely accelerate at a constant rate. The acceleration itself accelerates. The expansion rate grows without bound in finite time. If the Big Rip scenario is real, then the timeline is roughly as follows. About 22 billion years from now, about 60 billion years from now, depending on exactly how fast dark energy strengthens. The expansion will become so powerful that it begins to overwhelm gravitational binding. First, galaxy clusters will be torn apart. Individual galaxies will fly away from each other even within formally bound clusters. Then, months before the final moment, individual galaxies will be torn apart. Stars will be ripped from their galactic orbits. Then, minutes before the end, stellar systems will be disrupted. Planets will be torn from their stars. Then, fractions of a second before the final moment, stars themselves will be torn apart, then planets, then atoms. In the last instant, even atomic nuclei and subatomic particles will be ripped apart by the expansion of space. The universe ends not in a gradual fade, but in a catastrophic shredding of all matter at all scales, down to the most fundamental level. Current observational evidence slightly favors the cosmological constant scenario over phantom dark energy, but the measurements are not precise enough to completely rule out the Big Rip. Future observations, particularly from dedicated dark energy surveys like the Euclid Space Telescope launched by ESA in 2023, will help narrow down the equation of state of dark energy and determine which fate awaits us. There is also a third possibility, one that offers a more cyclical, perhaps even hopeful picture. This is the idea that the universe might undergo cycles of expansion and contraction, with big bangs followed by expansion, followed by some form of contraction or transition, followed by another big bang. One version of this is the ekpyrotic model, inspired by string theory, where our universe is a membrane floating in higher dimensional space, and big bangs occur when membranes collide. Another version is conformal cyclic cosmology, proposed by Roger Penrose, where the heat death of one universe, in which all matter has decayed and only massless particles remain, is mathematically identical to the conditions of a new Big Bang, allowing the universe to restart in an eternal cycle. These cyclic models are speculative and lack the strong observational support that the standard expanding universe model has. But they represent fascinating theoretical possibilities that remain under active investigation. They offer the poetic possibility that the expansion we observe, the superluminal recession of distant galaxies, might not be the final word, but merely one phase in an eternal cycle of cosmic renewal. Now let me bring us back to the quantum realm one more time, because there is a profound connection between quantum mechanics and the expansion of space that I want to explore. This connection involves one of the most famous quantum phenomena, entanglement. Quantum entanglement occurs when two particles interact in such a way that their quantum states become correlated, regardless of the distance between them. Measuring one particle's state instantly determines the other's state, no matter how far apart they are. Einstein famously called this spooky action at a distance, and found it deeply troubling. But decades of experiments have confirmed that entanglement is real. Now here is the question. What happens to entangled particles when the expansion of the universe separates them at superluminal speeds? Does the expansion break the entanglement? Can entanglement survive superluminal separation? The answer, according to our best current understanding, is that entanglement persists regardless of expansion. The quantum correlation between entangled particles is not a signal traveling between them. It is a property of their shared quantum state. It does not require ongoing communication or connection. Once established, the correlation simply exists, independent of distance or expansion. Two entangled particles on opposite sides of the observable universe, separated by superluminal recession, remain entangled. Their measurement outcomes will remain correlated if you could ever compare them. Of course, comparing them requires communication, which is limited by the speed of light, which means for particles beyond the cosmic event horizon, you can never verify the correlation. The entanglement exists in principle, but becomes permanently unverifiable in practice. This leads to a fascinating theoretical insight. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a remarkable conjecture known as ER equals EPR. Here, ER refers to Einstein-Rosen bridges, which are wormholes, and EPR refers to Einstein-Podolsky-Rosen entanglement. Their conjecture proposes that any two entangled particles are connected by a microscopic wormhole, a tiny bridge in spacetime. If true, this means that the fabric of spacetime itself might be stitched together by quantum entanglement. Spacetime and quantum entanglement would not be separate phenomena, but two manifestations of the same underlying structure. If this conjecture is correct, then the expansion of space and the structure of quantum entanglement are deeply intertwined. The expanding universe is not merely stretching a passive fabric, it is reorganizing the quantum relationships that give rise to space itself. This is speculative, frontier-level physics, but it suggests that understanding expansion at the deepest level will require unifying quantum mechanics and gravity, the long-sought theory of quantum gravity. Let me now address a question that many thoughtful people ask when they hear about cosmic expansion. If the universe is expanding, what is it expanding into? This question feels natural and intuitive, but it is based on a misconception. The universe is not expanding into anything. There is no pre-existing space outside the universe that the universe is filling. Space itself is what is expanding. There is no outside. This is difficult to visualize because our brains evolved to picture objects expanding within a larger surrounding space. But the universe is not an object inside something else. The universe is everything. When we say space is expanding, we mean that the distances between all points within space are growing. We do not mean that there is some boundary of space pushing outward into a void. There is no boundary. There is no void. There is only space, and it is getting bigger in the sense that distances are growing. An analogy might help, though all analogies are imperfect. Consider the surface of a balloon being inflated. An ant living on the surface of that balloon would notice that all other ants are moving away from it, with farther ants moving away faster. But the ant cannot point to an edge of the surface and say the surface is expanding into something beyond the edge. The surface has no edge. It is finite, but unbounded. It is simply growing. The ant's entire universe is expanding without expanding into anything external. Our three-dimensional universe may be analogous. If it has positive curvature, it could be finite but unbounded, like the balloon surface but in 3 dimensions. If it is flat or negatively curved, it could be infinite. Having always been infinite and simply becoming more spread out everywhere. In neither case does the expansion require an exterior. The universe is self-contained, and expansion is an internal property. Now I want to talk about something truly remarkable. We have discussed how the universe is expanding and how distant parts are receding faster than light. But there is a subtlety about the recession that is often overlooked. The recession velocity depends on the observer. What looks superluminal from our perspective does not look superluminal from the perspective of the receding galaxy. Consider Galaxy X, which from our perspective is receding at twice the speed of light. An observer in Galaxy X does not feel like they are moving. They are at rest in their own local space. If they look back at us, they see us receding at twice the speed of light. From their perspective, we are the ones moving superluminally. And both perspectives are equally valid. There is no preferred frame. No one is really moving. Space between us is expanding, and both observers see the other receding. This is the perfect symmetry of cosmological expansion. It has no center, no preferred location, and no preferred direction. Furthermore, consider a Galaxy Y that lies between us and Galaxy X, exactly halfway. From our perspective, Galaxy Y recedes at the speed of light. From Galaxy X's perspective, Galaxy Y also recedes at some fraction of the speed of light. From Galaxy Y's perspective, both we and Galaxy X are receding at the speed of light in opposite directions. But here is the key. From Galaxy Y's perspective, are we and Galaxy X receding from each other at twice the speed of light? In special relativity, you cannot simply add velocities like this. But in the context of cosmological expansion, the recession velocities do add up in this way, because they are not relativistic velocities through space, they are expansion rates. And expansion rates do add linearly without limit. This is another way to see why superluminal recession does not violate special relativity. Recession velocities in an expanding universe are not the kind of velocities that special relativity constrains. They live in a completely different conceptual framework. Let me now discuss the topology of the universe, which is a fascinating related topic. Topology is the study of global shape and connectivity. The geometry of the universe, whether it is flat, positively curved, or negatively curved, tells us about local properties. But topology tells us about global properties, like whether the universe wraps around on itself. Consider again the analogy of the balloon surface. A flat piece of paper and the surface of a torus can both be locally flat. They have the same geometry at every point, but they have different topologies. On the paper, you can walk forever in one direction and never return to your starting point. On the torus, if you walk in certain directions, you eventually loop back to where you started. The local geometry cannot distinguish these two cases. You need global information. Similarly, our universe could be flat geometrically, but have a topology that makes it finite. Space might wrap around in some or all directions. If it does, then light traveling far enough in one direction would eventually return to its starting point, like circumnavigating the globe. We might be able to detect this by looking for repeated patterns in the cosmic microwave background. Extensive searches have been conducted, and so far no such repetition has been found, placing lower limits on the size of any such wrapping. If the universe does wrap around, it must do so on a scale much larger than the observable universe. If the universe wraps around and we do not know it, this has interesting implications for the expansion discussion. In a spatially finite universe, the expansion is not creating infinite amounts of new space. It is taking a finite space and making it larger. But even in this case, for sufficiently large wrapping scales, all the same physics applies. Distant regions recede superluminally, horizons exist, and the observable universe is bounded. Now let us discuss a fascinating thought experiment that illuminates the strangeness of cosmic expansion. Imagine you are standing in deep intergalactic space, far from any galaxy, with a powerful laser. You point the laser at a very distant galaxy currently receding from you at, say, 1.5 times the speed of light, and you fire. Will the laser light ever reach that galaxy? Counterintuitively, the answer is, it depends on whether the expansion is accelerating or decelerating. In a decelerating universe, even though the galaxy is currently receding superluminally, the expansion will slow down over time. Eventually, the recession velocity of that particular distance will drop below light speed, and your photons will be able to make progress and eventually arrive. In a decelerating universe, there is no cosmological event horizon, and every point in the universe is eventually reachable. But in our universe, with its accelerating expansion, the answer is different. If the galaxy is currently beyond our event horizon, then your laser light will never, ever reach it. The expansion will carry the galaxy away faster than your photons can approach. Your photons will travel at the speed of light forever, making progress locally. But the space in front of them keeps expanding too quickly. They will be like a swimmer caught in a current that is accelerating. They can swim with all their strength, but they will be swept backward, farther and farther from their destination, for all eternity. If the galaxy is beyond the Hubble sphere but still within the event horizon, something more subtle happens. Your photons, upon being emitted, will initially be swept backward by expansion, moving away from the galaxy in spite of traveling toward it. But over time, as the photons enter regions of space closer to you, where the expansion rate is lower, they begin making net forward progress. Eventually, they cross the Hubble sphere of the destination galaxy and arrive. This is genuinely bizarre. Light that is initially moving away from its target, being pushed backward by expansion, can nonetheless eventually arrive if conditions allow. It is a beautiful example of how non-intuitive expanding universe physics can be. Let me now bring us to another angle of this story. I want to discuss what happens at the quantum level during expansion. Specifically, I want to talk about how expansion affects the quantum vacuum and gives rise to real physical phenomena. One of the most remarkable predictions of quantum field theory in curved spacetime is that expansion can create particles from the vacuum. In flat, non-expanding space, the vacuum is a stable state with no real particles. But when space expands, especially if it expands rapidly, the vacuum of the earlier time is no longer the vacuum of the later time. What was empty space before expansion has become populated with real particles after expansion. The expansion itself has extracted particles from the quantum vacuum. This phenomenon is directly responsible for the origin of all structure in the universe. During cosmic inflation, the quantum vacuum fluctuations, tiny random fluctuations in the energy density of empty space, were stretched to macroscopic and eventually cosmic scales by the exponential expansion. These fluctuations, once submicroscopic, became the seeds of all large-scale structure. The slightly overdense regions attracted more matter through gravity, eventually forming galaxy clusters, galaxies, stars, and planets. The slightly underdense regions became the vast cosmic voids we observe today. The pattern of hot and cold spots in the cosmic microwave background is a direct imprint of these quantum fluctuations, stretched by inflation from the smallest possible scales to the largest observable scales. Think about this for a moment. Every galaxy, including our own Milky Way, exists because of a quantum fluctuation that was amplified by superluminal expansion during inflation. Every star, every planet, every living being owes its existence to the combination of quantum randomness and cosmic expansion. The structure of the universe is quantum mechanics writ large. Literally, a related phenomenon is the Unruh effect, predicted by William Unruh in 1976. An observer accelerating through the vacuum does not perceive emptiness. Instead, they perceive a bath of thermal radiation with a temperature proportional to their acceleration. This is related to Hawking radiation from black holes and has deep connections to the expansion of the universe. In an expanding universe, the cosmic event horizon emits radiation similar to Hawking radiation from a black hole, with a temperature determined by the expansion rate. This radiation is extraordinarily faint, far too faint to detect with current or foreseeable technology, but its theoretical existence illustrates how expansion affects the quantum vacuum in measurable ways. Now let me address something I find particularly fascinating: the relationship between cosmic expansion and the arrow of time. Why does time seem to flow in one direction? Why do we remember the past but not the future? Why does entropy, the measure of disorder, always increase? These questions are among the deepest in physics, and cosmic expansion may play a role in the answer. The second law of thermodynamics states that the entropy of a closed system never decreases. Things go from ordered to disordered, never the reverse. But this law is puzzling because the fundamental laws of physics are time-symmetric. They work the same forward and backward. If you filmed a collision between two particles and played it in reverse, both versions would obey the laws of physics perfectly. So where does the asymmetry come from? Why does time have a direction? One answer, proposed by many physicists including Roger Penrose and Sean Carroll, is that the arrow of time exists because the universe started in an extremely low entropy state at the Big Bang. The Big Bang was extraordinarily ordered, extremely smooth, extremely uniform, with almost no gravitational clumping. This is a very special, very low entropy initial condition. Ever since, entropy has been increasing as the universe evolves toward its maximum entropy state, the heat death. Cosmic expansion plays a role here because it provides the vast reservoir of available entropy that the universe has been filling. As the universe expands, the maximum possible entropy increases. The actual entropy increases too, but it chases an ever-growing maximum. The expansion continuously creates new room for disorder, maintaining the entropy gradient that we experience as the arrow of time. Without expansion, it is possible that the universe would have reached maximum entropy long ago, and the arrow of time would have disappeared. This connection between expansion, entropy, and the flow of time is still debated and not fully settled. but it suggests that the expansion of the universe may not just be responsible for carrying galaxies apart. It may be fundamentally responsible for the very existence of time's direction, for the fact that events happen in a sequence rather than in a static timelessness. Now I want to bring us back to concrete observational science and discuss how we actually measure the expansion of the universe in practice. I have mentioned supernovae and Cepheid variables, but the full toolkit is much broader and more impressive. The cosmic distance ladder is a sequence of techniques, each calibrated by the one below it, that allows astronomers to measure distances from nearby stars all the way to the edge of the observable universe. The first rung is parallax, as the Earth orbits the Sun. Nearby stars appear to shift slightly against the background of distant stars. This geometric shift gives a direct distance measurement for stars within a few thousand light-years. The Gaia satellite, launched by ESA in 2013, has measured parallaxes for over 1 billion stars with unprecedented precision, providing the foundation for all subsequent distance measurements. The second rung uses stellar brightness relationships. Cepheid variables, which pulsate with periods proportional to their luminosities, serve as standard candles out to about 100 million light-years. RR Lyrae stars serve a similar purpose for older stellar populations. The tip of the red giant branch method uses the maximum brightness of red giant stars, which is remarkably consistent, as another distance indicator. The third rung uses Type Ia supernovae, which I discussed earlier. Because these thermonuclear explosions have standardizable peak luminosities, they can be used as distance indicators out to billions of light-years, far enough to directly measure cosmic expansion and its acceleration. Beyond supernovae, there are additional techniques. Baryon acoustic oscillations use the characteristic scale of sound waves in the early universe, frozen into the distribution of galaxies, as a standard ruler. This scale, about 500 million light-years in the present universe, provides a distance measure that is complementary to and independent of supernovae. Gravitational lensing time delays, surface brightness fluctuations, and the kinetic Sunyaev-Zeldovich effect all provide additional independent measurements. Each of these techniques has been developed, refined, and cross-checked over decades. Together, they build a consistent picture of an expanding, accelerating universe, with the superluminal recession of distant galaxies being an inescapable mathematical consequence of the measured expansion rate. Let me now discuss an interesting historical angle. The idea of an expanding universe did not begin with observations. It began with theory, with equations that predicted expansion before anyone observed it. In 1922, 7 years before Hubble's observations, Russian mathematician Alexander Friedmann solved Einstein's field equations for a homogeneous, isotropic universe and found that static solutions were unstable. The universe must be either expanding or contracting. Einstein initially rejected Friedmann's work, publishing a note claiming it contained a mathematical error. He was wrong, and later retracted his criticism. But he remained philosophically committed to a static universe and introduced the cosmological constant specifically to prevent his equations from predicting expansion. Independently, in 1927, Belgian priest and physicist Georges Lemaître also derived the expansion from Einstein's equations and went further, proposing that the universe had originated from a single point, a primeval atom. He even estimated the expansion rate from early redshift data, obtaining a value remarkably close to what Hubble published 2 years later. Lemaître's contribution was largely ignored at the time, partly because it was published in a less prominent journal and partly because Lemaître himself was modest about promoting his work. History gave Hubble the credit for discovering expansion, but Lemaître deserved equal recognition for predicting it theoretically and deriving it observationally. In 2018, the International Astronomical Union officially renamed Hubble's law to the Hubble-Lemaitre law in recognition of Lemaitre's priority. The reluctance to accept expansion, even among the greatest physicists, tells us something important. The idea that space itself is growing, that distances between objects increase even when nothing is pushing them, is genuinely counterintuitive. It violates our everyday experience so profoundly that even Einstein resisted it. Yet the evidence is overwhelming. The expansion is real, it is accelerating, and its most distant manifestation is superluminal recession. Now let me delve into one more fascinating area. How does expansion affect the propagation of gravitational waves? Gravitational waves, ripples in space-time predicted by general relativity, and first directly detected by LIGO in 2015, travel at the speed of light. As they travel through expanding space, they experience cosmological redshift, just like electromagnetic radiation. Their wavelengths stretch with the expansion, and their frequencies decrease. This means that gravitational waves from distant sources are redshifted, and the amount of redshift tells us about the expansion history of the universe along the path of the wave. In the future, gravitational wave detectors could provide an entirely independent measurement of cosmic expansion. The LISA space-based gravitational wave observatory, planned for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers at cosmological distances. By measuring both the gravitational wave signal and any electromagnetic counterpart, astronomers will be able to construct an entirely new measurement of the Hubble constant, potentially resolving the Hubble tension with a completely independent method. Gravitational waves also raise an interesting conceptual point about superluminal recession. If a gravitational wave is emitted by a source that is currently receding faster than light, can the gravitational wave ever reach us? The answer is exactly the same as for light. Gravitational waves from sources currently beyond the Hubble sphere can still reach us if those sources were within the Hubble sphere when the waves were emitted. And gravitational waves emitted by sources currently beyond our event horizon will never reach us. The expansion treats gravitational waves and electromagnetic waves identically, because both propagate at the speed of light through local space. Let me now bring us to a philosophical but scientifically grounded meditation on what all of this means for our place in the cosmos. The superluminal expansion of the universe means that we are fundamentally, permanently, inescapably isolated from almost all of reality. The observable universe, vast as it is just a tiny bubble in what may be an infinite or nearly infinite cosmos. And even within our observable universe, the vast majority is already unreachable. We exist on a small planet, orbiting an ordinary star in a typical galaxy, inside a cosmic horizon that limits not just our vision, but our influence. Nothing we do, no signal we send, no spacecraft we launch, can ever affect or be affected by most of what exists. We are causal islands in a universe that is being pulled apart. Some find this isolating, others find it liberating. From a scientific perspective, it simply is what it is. The universe operates according to its laws regardless of how they make us feel. The expansion does not care about us. Dark energy is not malevolent, it is simply a property of space. But acknowledging the reality of our cosmic isolation is important because it forces us to grapple with fundamental questions about the nature of knowledge and existence. If we can never observe or interact with most of the universe, does that unseen portion exist in any meaningful sense? This is not merely a philosophical question. It has real implications for how we do cosmology. Inflation predicts that the universe extends far beyond what we can see, and that the physics is the same everywhere. But we can never verify this directly. We accept it as the simplest, most consistent interpretation of our observations. But epistemic humility requires acknowledging that we are making assumptions about regions forever beyond our ability to test. Now let me bring together all the threads we have been exploring. The edge of the universe moves faster than light because the expansion of space is not subject to the speed limit that governs objects moving through space. Einstein's special relativity prohibits superluminal motion through space. Einstein's general relativity not only permits, but predicts superluminal expansion of space. These are not contradictory statements. They apply to different physical phenomena. The expansion was first predicted theoretically by Friedman and Lemaitre in the 1920s and confirmed observationally by Hubble in 1929. The acceleration of the expansion was discovered by Perlmutter, Schmidt, and Ries in 1998, revealing the existence of dark energy. This acceleration means that the expansion rate is increasing with time, causing more and more of the universe to recede beyond our causal reach. The mathematics of expansion, encoded in Hubble's law and the flow metric, guarantees superluminal recession beyond the Hubble sphere. The observable universe is a finite bubble in a potentially infinite cosmos, bounded by horizons that are shrinking due to acceleration. We can see ancient light from galaxies now receding at multiple times the speed of light, because that light was emitted when those galaxies were closer and their recession was subluminal. Dark energy, comprising 68% of the universe's energy content, drives the acceleration through its negative pressure and non-diluting energy density. Its fundamental nature remains one of the great unsolved problems in physics, connecting to the cosmological constant problem, the vacuum energy crisis, and the need for a quantum theory of gravity. The quantum vacuum plays a crucial role in expansion, both as a possible source of dark energy and as the origin of cosmic structure through inflationary amplification of vacuum fluctuations. The interplay between quantum mechanics and cosmic expansion is one of the most active frontiers of theoretical physics, with implications for our understanding of space-time itself.